Reaching the kind of almost end of the session now. Yes, is it fine? So, I had talked about Einstein-Podolsky-Rosen paradox, that is against quantum theory, and what Einstein-Podolsky-Rosen paper concludes is that there should be an alternative theory. Correct theory is fine, but it's not complete, so we should look for a alternate theory is the conclusion. So how alternate theory came is the next thing. EPR paradox, Einstein-Podolsky-Rosen paper came in 1935, but till 1965 there was a gap. So people did talk about EPR paper, almost overall coffee and philosophical discussions were happening. How it converted into a real discussion and went ahead is what I am going to tell you next. That is, the EPR debate took a new twist in 1964. How? So, long after Einstein's death, unfortunately Einstein was not there, his paradox was continued by John Bell. So, Bell resolved by thinking of entanglement as an entirely new kind of phenomena, which he termed non-local in the sense, so if you have two systems which are separated and one system disturbing the other, one measurement disturbing the other, I told you it is possible by some kind of an entangled state. Once you have an entangled state, what is done here will disturb the other part. So that observation, Bell named it as non-local. Local is what happens here is here only. Non-local is it can even influence the other party. So he used the word non-local, and in 1964 he was, after a year's leave from CERN, he was working in CERN, he went on a sabbatical leave, then he took to his what is close to his heart, he worked on EPR paradox basically. That is, when he was, while he was at CERN, he was doing something which is demanded by everybody. When he was left alone, he started doing what is EPR paradox, how to think about it. He was a big fan of Einstein also. So he wanted Einstein to get it resolved. So what the paper is on the Einstein-Podolsky-Rosen paradox, J.S. Bell, 1964. And this is just a picture of him. And what he argues, let us come to his argument. So he says, if I take a system of two spin half particles, what we call as a 2-qubit system now, take it in this particular way, quantum mechanics does not permit us to assign precise numerical values to all spin components because it is not allowed, not non-commuting observables. So suppose I assume a theory involving some hidden variable, he calls it as hidden variable. So now to understand a hidden variable, I think about it in this particular way. For example, if you take statistical mechanics of several atoms, gas molecules are there. So in mechanics, I would be able to study each individual atom or molecule as a particle, and I will solve Newton's equations, fine. But if I have, say, a collection of them, I will not be able to study them. But what I will do is, I will give a probability distribution for velocity in Maxwell's probability theory. That is, probability depends on velocities, and velocities are varied. If you remember, Maxwell's probability distribution is used in the statistics that you have learned. So like that, there, velocity is a hidden variable. And I don't get velocity of each individual particle, I don't get it. So people thought, Bell thought that there is a hidden variable underlying quantum physics. So I will be able to get results of quantum physics using hidden variable theory. I should not use quantum theory. I should not have anything to do with non-commuting observables and all that. How do I test it? He created a toy model. That is, for one particular problem, I will create a toy model. For this, if it works, then I will think about a bigger theory. That is like, for a given situation, I will construct a hidden variable model. If it works, my theory prediction works, then I will, let us continue to construct that theory for entire physics, for example. But otherwise, if it fails, then I have to give up my attempt. So he believed in his picture. What he said, imagine a theory involving some hidden variable which I don't know. I don't know its property. Like in gas molecules, I said take velocity as a hidden variable. All probabilities depend on P of V. Probability depends on P of V. It's a normal distribution. If you check it, all that is something which we have done in statistical mechanics. He thought it is a hidden variable theory. Given the lambda, we suppose that the spin components of the system A and B in their respective directions have well-defined numerical values. What I am trying to tell you is, this is written fine. Quantum theory does not allow any spin components, two different spin components, say simultaneous realities. It can't give you. But I assume in my hidden variable theory, depending on the hidden variable, I can talk about its spin components, precise values of spin components, which is not there in quantum mechanics. It is there in my hidden variable model. That's what is the kind of assumption that I do. And when I take it, they are all known. And what are the values for the spin components? In quantum theory, I take it to be +1, -1, plus half, minus half, but I don't take the half. We will take 1 and -1, that works for me. If I take a variable operator whose eigenvalues are plus or -1, that is what I will take. So in hidden variable model, I call it spin component, but I don't use quantum theory. So I will say these spin components do indeed have the value, say for a particle in the direction A, that is spin component is in the direction A, given lambda, whatever, depending on the value of lambda, it takes values only plus or -1. That is in this direction A. Lambda value, I can assign that. Don't think about how it will work, but these are two dependent variables. Which direction and what is the hidden variable? It depends on that. Similarly, B of B lambda can assume plus or -1. So these values are assigned irrespective of measurements, means it exists. Like what Einstein said, nature should have physical reality. Whatever physical realities are there, my theory should have it imprinted in my theory. So hidden variable theory says, I have a hidden variable lambda, and based on the value of hidden variable, I will assign spin components without using quantum theory. I will say these are well-defined values. It is there in my theory. That's what is taken. No experiments, no need to do anything. Still, it should exist. Otherwise, it's not an objective reality. I will take it. So once I take it, Bell defines definite values for A and B can be assigned for spin components along arbitrary orientation. What I said is argument. That's called realism. That is, I want realities to exist. Einstein wanted local realities should be there in our system. So it is there, is first assumption or argument. The locality means the numerical value A of A lambda. If you get +1 or -1, it does not depend on B of B lambda. What happens to B is not going to affect A of A lambda. They are independent realities in that sense, is what he is saying. Not using quantum theory. Again repeating, no quantum theory here. So if I do that, what I will do now is, I will take, hidden variable is there. I need to do an average over the hidden variable, like probability for velocity, Maxwell distribution. I have to integrate. That's what is my real result. That is, if I have many particles, I have to do a averaging. Like that, that kind of a theory is what I am taking. Mathematical model says, I have a probability distribution for the hidden variable. I don't have a physics of what is lambda, but I will assume that there is a row of lambda which is a probability. If it is a probability, then integration over row of lambda should be 1. That is probability theory. I am only using probabilities, and I will say that row of lambda probability lies between 0 and 1. That's my theory. That is, I am using no physics, but only a mathematical model. That's a tau model, that too, for spin components. So now once I do it, correlations between A spin and B spin, how do I define it is the next question. In hidden variable model, I will say A of A lambda is what I obtain experimentally if I do. B of B lambda, I obtain what is there. What are the values they take? Plus or -1. But depends on lambda. So I have to integrate it over this, and I call this correlation of two spin components. One is A hat, that is unit vector, B unit vector. This is the definition of what I call as correlation between two. That is, if I make a measurement of spin component at A slab and B slab, I will note down the values. Then after they finish the experiment, they come together. We will write down for lambda this is 1, that is minus 1, this is 1, that is minus 1, and then I add it. Okay. So this batch I will take a height measurement, and then I will take a height measurement here. Then I will check whether there is a correlation. It won't be, but here it will be. So I will do, depending on the probabilities, I am doing this kind of a calculation. Once I do this, what I will now say is, Bell chose a different thing. This is done by CHSH, which I didn't mention. Clauser, Hahn, Shimoni, and Halt. They altered the Bell argument to write a different inequality. So I chose this because it is much easier to explain. So this is a Bell inequality. But what they did is choose 4 different unit vectors. That is, I have to take spin components along one direction for A, one direction for B is what I told you. Let us choose 4 different unit vectors in this model. So I will write A prime, B prime, and I will obtain the following inequalities for the linear combination of correlations. That means I choose some particular correlations. What? I have defined what is CAB. It is D lambda, rho lambda, A, B, correct? And what is C, AB prime? It is same thing, but with a B prime here. Earlier I have told what is CAB. So it is a CAB minus C of AB prime. That is going to be AA, BB and AA, BB lambda. How do I obtain it? We will come to it later on. But I take the combination like that. And from my mathematical model, it's very clear that this quantity is less than or equal to only B of B lambda. How? I will explain it. Suppose you have an integral and you have a quantity. If you take in an integral, if you write the maximum value of the quantity everywhere. So if you write maximum value of, let us say, this quantity, otherwise it will be plus 1, minus 1, plus 1, minus 1 everywhere. But you will write always plus 1, let us say. It's larger than whatever is there earlier, whatever we have. Obviously, when I write the highest value allowed for one quantity, the modulus of it will be less than. That is what I do. This quantity is mathematically always less than or equal to this one, where I substitute A of A lambda to be its maximum value, that is 1. So then it is fine, no? This works mathematically. So then I will say, same way I take A prime B. Here I took A and B prime, but A is fixed. So that means I am doing experiments with unit vectors A, B and B prime. Here I will do A prime, B and B prime here. A prime, B prime. No A. That's my choice. He chose that appropriately. Once you do it, again the same thing. A of A prime lambda and B prime. There will be a plus sign now. Chosen. So this is always less than or equal to only what is there inside the bracket. So that is very obvious, because in any integral that you have, the 2 modulus is taken, and the quantity, if you take highest value, you will get larger value than what it is. That's all is used here. So once I write this, I add these 2 inequalities, one less than this, other one less than this, and what I get is C of AB minus C of A prime B prime, this one. What do you get here? This 2, if you add this, B of B lambda is this, and this one will get cancelled. So I am going to get rho lambda, D lambda, B minus B prime, B plus B prime. But whatever is on the right hand side, I am only going to have B of, what is that? 2 times, okay. B of B prime lambda gets cancelled. I have 2 times B of B lambda. 2 times B of B lambda will appear. I didn't write it here, but you will all see that this plus this is 2 times B of lambda. This will go away with what is the minus and plus sign. Once I do it, I get 2 times B of lambda. There is an integral again. Highest value you write for B of lambda. What will be left there? B of lambda is taken as 1. Then I have an integral d lambda rho lambda. That's all. 2 times. So it will be integral rho lambda d lambda is 1. It is a probability. So I get this is less than or equal to 2. I should have written less than or equal to. So I should write this is less than or equal to 2. Am I right? That's called the Bell inequality. So he never used quantum mechanics. He defined what is called as correlations. Correlations of two separated parties if you do measurements using local real hidden variable model. Local, no non-locality, real. Reality is assumed. And I am doing constructing correlations. This is what is inequality, and this inequality should be obeyed by all local real hidden variable models. That means what Einstein likes as a good theory, it will obey this kind of a inequality. That's all is the idea. So now I come to simple approach for understanding. Let me write something like this: A1 B1, A1 B2, A2 B1 minus A2 B2, where A1 is an observable which takes values plus 1 minus 1. A observable means head tail kind of a observation. Head is plus 1, tail is minus 1. We will take that. Suppose I write A1 is plus minus 1, B1 is plus minus 1. I don't want to write a hidden variable and all that mathematics, so I will simply write it like this. This could be expressed as A1 into B1 plus B2 plus A2 into B1 minus B2. There is an average. Average about any probabilities. Let us take it about any probabilities. If I write this, this should be less than or equal to 2. How do I understand it? Let us keep on writing all possible values. Take this one, A1, B1 plus B2. Inside the average you have this, but fine. Let us take one value. A1 is 1, B1 is 1. Like that I keep writing. Let me say B1 can be, B1 is, they are all a plus or minus 1. That's a toy model we are playing. So if B1 is equal to B2, that means it's either plus 1, both of them are plus 1, or both of them are minus 1. Let us take it. Then this term goes away because B1 is equal to B2. So this term goes away. What is this term? B1 plus B2 will be 2, plus or minus 2. So I have plus or minus 2 into A1. A1 is plus or minus 1. So this will be plus or minus 2 always. That is when I calculate it. If B1 is not, B1 is equal to 2. And I have a modulus. So that is equal to 2. If I take only at one time, once I take it and I demand that if B1 is equal to B2, I get value 2, one trial. So like that I keep doing several trials. B1 is equal to B2, B1 not equal to B2. Suppose I take B1 not equal to B2, this term will have 2. B1 is plus 1, B2 is minus 1. So let us say B1 is not equal to B2. It will be plus or minus 2 again. So then this term will go away. B1 is not equal to 2. So this term will go away. And this will give you plus or minus 2. Forget average. I am writing one trial, single trial. So in single trial, the value will be 2. Always 2. Suppose I take B1 is equal to 2. So other time I will take B1 not equal to. In all the cases I get 2. Okay. And then I take an average of all results that I get. Average of any quantity cannot be larger than the actual value. That is if I write 2. That is like saying I have all of you, I take average height, let us say. Okay. Maximum height here may be say something like 6.2 feet, let us say. My average value cannot be larger than 6.2. That's the idea here. I can't find larger than what is found in individual trial too. That's all is highest. That's the way you can argue without doing your hidden variable model. But hidden variable model has a content, which I just want to tell you this. So I will say, this is like an experiment. I have a source which creates two particles, A spin and B spin, and I have measurements. A1 and A2 are like spin component in the direction A, spin component in the direction A prime. At Alice's end, I do A1, A2 means it is spin component A of A prime, A of A, two measurements. So I get plus or minus 1. I keep recording. And B, B1 and B2, I keep recording. So two ends, I do 4 different measurements. A at Alice's end, B and B prime at Bob's end, and then here at B prime, total all the measurements are recorded. Once I do it, now I take what is quantum theory. Quantum theory too talks about what is spin component. There is a wave function. I can calculate what is correlation. How do I calculate? I told you, operator spin component of A has an operator. Spin component of B has an operator. I take a tensor product of the two and then take an average. I can do it. I am only showing the result of such measurement, not calculating it here. Okay, so it can be calculated, and the result is quantum mechanical. In this particular state, if I take, I make a measurement of spin component using quantum theory, not using local hidden variable theory. So I get minus A dot B. That means cos theta, angle between what is A, what is B. I have set my measurement to be in a direction A and there in a direction B. So direction A and direction B, angle between the two will come if I do a quantum mechanical calculation. I know to do it. Hidden variable model, I don't do any calculation. I will say there is a inequality. This is less than or equal to 2. That's all I will say. I don't have individual values. Theory sets a bound on combination of correlations. That's all is what I am saying. But quantum mechanics, I can sit and calculate given a state and given a operator. So now, I want to show that this Bell-CHSH inequality that I wrote, in quantum theory, it gets violated, which tells me that quantum theory is not a local real theory. That's all. I will repeat again. Is quantum mechanics a good theory? So Einstein's Podolsky-Rosen paper says it's not a complete theory. Done and over. So if it is not a complete theory, let us take an alternate model, that is local hidden variable model. Hidden variable model gives you a inequality. Every local hidden variable model should obey that inequality. If it doesn't obey, I will say it's not a local hidden variable model. So now I will show you quantum theory, of course, is not a hidden variable model. Means it violates the inequality. It's not a good model for quantum theory. That's what is said. So now let me choose A and B, my measurements, A and B, angle between A and B to be cos pi by 4. A dot B is cos theta. Angle between A and B, I will choose it to be pi by 4. I have written it here. A, B. I choose this geometry pi by 4. I know what is the value, 1 over root 2 for this. And I choose A, B, A prime, B prime. What is B dot A prime? That is also 1 by root 2. And what is A prime, B prime? That is also 1 by root 2. But what is A, B prime? If I take A, B prime, that is going to be 125. It will be minus 1 by root 2. If I check what is A, B prime, that will be minus 1 by root 2. So now I will write A, B is 45 degree. A, B prime is 135 degree. 45, 45, 90, 90 plus 45 is 135. So I write all the angles, and now I will write what is cosine 45, cosine 45, cosine 45. But this one will be minus 1 over root 2. 1 over root 2 minus of minus 1 over root 2 is plus 1 over root 2. So I have 1, 1, 3, 4 times 1 over root 2. It will be 2 root 2. Is 2 root 2 larger than 2? 2 root 2 larger than 2 or less than 2? It is larger than 2. So it is violated. So quantum mechanics says correlation is A dot B. Correlation value is A dot B. And I choose A, B such that it gets violated. So once I say that, now I have whatever source and measurements and all that, it gives you 2 root 2 value is shown in quantum theory. So it is not going to be a local hidden variable model is proved. So I will now take a war between two theories. That is, I have quantum theory on one end, I have local hidden variable models at one end. If I do an experiment, it's not an experiment to prove something for technological use, but it is foundational between two theories which will win. So this is kind of a experiment. So in such an experiment, so first it was done by Clauser, but I have just not shown every detail here. So in 1972, the first of many experiments that I have shown that a violation of Bell inequality is seen, which means if I do an experiment, it is nature. Whether nature obeys local hidden variable model or nature obeys quantum theory. So it's violated. So it is a result which shows that you have a quantum theory, basically. So that is what it indicates. So Bell regretted that results of these tests did not agree with the concept of local hidden variable models. He was a fan of Einstein, and he says it's a pity that Einstein's idea does not work. The reasonable thing just doesn't work. So I want to tell you what is reasonable for us is not that agrees with what we have. So we have to improve our thinking and how to accept it. That's what is the thing. So now this is something just to indicate, but I don't give you clear this thing. So the plot like line here is hidden variable model, but this is not a clear example, but that's what David Mermin published in Physics Today. I just took that kind of a caricature to show here. This line is quantum mechanics and points are experimental. That is, it's not agreeing with here local hidden variable model. So now, all right. So this is next. The first what was done was by Clauser, and Clauser did an experiment in his lab. He had to rotate one side angle to set it to A, and the other side he goes and sets it to B. So that is the way he did the experiment. Then people started, hey, this is not the good way. When I set A, B should not know that I have set it as A. So one shouldn't know the other. So you should set it independently. It should be random. What I do here should not be known to them. That you have not taken care. So it was done by Alain Aspect at R France. So he did the same experiment, and then Physics Today article. So I am just carried away by how people reacted to it. In Physics Today article, David Mermin names it as, is the moon there when nobody looks? That is what Feynman had said. That is Feynman had said that, I think, not Einstein. It is like Bohr and others of Copenhagen, they had mentioned that, see, quantum theory, you only get results only when you do an experiment. Before that, don't ask for what is reality. Quantum theory will not give you reality unless you finish an experiment. So, Einstein would think, if I don't look at moon, will he be there or not? So, that's what is the title given. So, it looks like moon will not be there if we don't look at it. That's the experimental result. So, our thinking has a limit, but quantum mechanics goes beyond that kind of a limit. That is the theory which is respected by nature. So, we have to modify our thinking is the lesson, that is philosophically speaking. So, I am just trying to show you this continued for till 2015. Bell inequality was first done 1972. But there were loopholes, varieties of loopholes. I just collected some cartoon to show this. That is, quantum mechanics proposes a universe which is at odds when our intuitive reality, that is, with our intuitive reality, quantum theory is at odds. So, some scientists, including Albert Einstein, have hoped that alternative theories with so-called hidden variables acting behind the scenes might explain away some of the quantum theory's weirdest implications and kill them away. We shouldn't want weird kind of things. So we remove them. Can we? Is the question. So until recently, no experiment could conclusively rule out local hidden variables, but in 2015, this changed. That means local hidden variable model was still holding this thing. What it said is, you have not closed the loophole. When I set A here, will be no, that should be cleared. So there other loopholes are also there. We have to control them. So till 2015, there was local hidden variable model had a edge. While Bell gave up on that, it still had a edge. So we would have still claimed that no, it is still our intuition may work kind of thing, but it failed is what is the thing. Einstein's objections to quantum theory rested on the two basic principles, that is realism and locality. We should have it. Otherwise, I am not happy. You should have realism. You should have locality. That is the main thing. Realism is the notion. Whatever I said, I am kind of consolidating here now. Realism is the notion that objects have deterministic properties. An apple, for instance, is red or it is yellow. That is, imagine that there are only two breeds of apple. Either it is red or it is yellow. It can't be red yellow. So that is what Einstein says as reality. That is, it should be crystal clear, red or yellow. So if you think like that, so locality is the idea that objects can only be influenced by their surroundings. Influences cannot travel faster than light. Every one of us agree with such things. But will quantum theory do that is the question. So now I will say, yet the theory of quantum mechanics suggests that reality is much weirder than that. So this is just to show in this kind of a picture some cartoon which I liked and I am showing it. So now, according to quantum mechanics, a particle can be in two states at the same time, which I have told you already. So it can be this kind of thing. Mind you, we do have both red and yellow. This kind of apple is not strange to us. What I am saying is, imagine only red or only yellow. If it is the allowed thing, then I don't have it. This doesn't mean that apple is quantum mechanical. Please don't think like that. It's only to use that explanation. So now, particles can even be entangled with one another. That is, if you look at one apple and find it red, the other instantly becomes yellow. No choice. State can be created. One is, if I check one yellow, other one I know it is red. So I know this is entanglement will only make it, not otherwise, is what we are saying. Yes? So now, Einstein refused to accept this concept, calling it spooky distance action at a distance. It's some kind of some ghostly things are acting, so spooky action. So that is what is doing it. Theory should not be like that. We should have only gods, not ghosts. So that is the kind of idea. So he claimed that there must be local hidden. He did not, but people now say that Einstein had in his back of his mind some hidden variables are there and all that. But these cartoons can talk anything. So unknown to observers, some hidden variables are not known to observables. After they get integrated, I have an average. That's what I see. But hidden to it, there is a hidden variable which I can assume and then I can give reality. I can give locality. So do it and check it. So now entanglement exists no matter the distance between particles. We should note it down. And then he says, Bell comes. The Bell discovered that quantum theory conflicts with any local theories. Conflict means he wrote an inequality that is for local hidden variable models. Quantum theory gives you violation of it. So these are in conflict between two theories are under conflict. Which decides it? A experiment. And experiment favors quantum theory. So that's the result now. So Bell's test, two observers would make separate measurements of two supposedly entangled particles, and Bell calculated the maximum amount of correlation that could arise between the two observers, finding of local hidden variable limited by the speed of light were at work. That is all whatever Einstein wanted was there in local hidden variable model, and he gave an inequality. So experimenters soon started to work putting the test into action. But two loopholes continued till 2015. They are called, one is called locality loophole. That is, the measurement situations are close enough to allow communication with each other at sublight speed during a test. That is, I am doing one here, and I am doing it. Then it can know. That is, I don't have ruled out locality loop. What is done here may affect this in that case. So aspects experiment was something like that. It is in a on a optical table. If you do on a optical table, that cannot be accepted. So, but you continue, do it further. So, other loophole was detection loophole. All our detectors are not 100% sure. They have detection inefficiency. So now I have to say detectors are only able to measure some, but not all the entangled particles. Some are lost. So if it is that, then whatever result I get, will it be able to prove that my theory is, it may not give me violation, then do I conclude that it is local hidden variable model? Or can I improve my detectors? No. I have to do something called as fair sampling and some such things. That is, my sample, I have to do a fair sampling assumption and then try to give you correct results after fair sampling. That is again a probability theory kind of analysis. These two loopholes were cleared in 2015 at Delft University of Technology, and with what? Two tiny diamonds were there. So this is what is called as nitrogen vacancy diamonds. So one had diamonds and the nearly perfect carbon lattice gives you diamonds, and one flaw is there, one vacancy is there. That vacancy is replaced by nitrogen. Today there are technically one can produce a nitrogen vacancy, that is a diamond with one nitrogen replaced. So such things in the nearby perfect carbon lattice, there exists a flaw. The occasional nitrogen atom appears, and in some places next to such a nitrogen atom, there is a carbon atom missing, and that is a defect center that can be created. So now this acts like a trap for electrons which are shared between in diamond lattice. So electron is trapped in the vacancy then. So if I have two such electrons have a spin up and down or a superposition, and if I create two such diamond atoms together, electrons will be entangled, but I can't make a measurement on electrons. But if I take them away and kind of tune the electrons by giving it excitation, it may go up and come down and give me a photon. So from electron, I will get it to photons. Photons are emitted, and when photons have come, I can do a measurement. Electrons cannot be measured. So people did the diamond lattice with such a trapped electrons there. Two electrons are entangled in here. When they are separated, we have an entangled state, fine. But to do a measurement, I have to have excitation of the atoms and then electrons, and then I should get a photon. So it is a two photon entanglement. I will prove all fair sampling. I will prove everything, and this is what is said. There is a photon coming, electron, photon coming. Here a photon is coming, and they are entangled. They travel across any distance. So even if I have separated, they did this experiment with 1280 meters. That's the experiment. That put a full stop to local hidden variable models, which means that we have to live with quantum theory. Let us start thinking quantum theory. And if I ask a question, it is because I have a constraint in my mind that this should be like this, that should be like this. But quantum theory is different. It is weird. I will only calculate and find it out and think what I need to do, but it's interesting. So how to deal with it? I still continue to think from a foundations of physics point of view and try to resolve it as we go on. But Einstein-Podolsky-Rosen paradox had some limitations in the sense they cannot define reality in a perfect way. They cannot talk about locality in that kind of a perfect way, because quantum theory allows entangled states, that is nature. So with that, all these assumptions will get killed. Locality, reality are my notions, but quantum theory has more power. That is, it can create such a state. So my intuition would have agreed with this, but there are something much more than that. Local real theories, quantum mechanics is not that. So we continue with, this is what is, the universe is conclusively weird. That's what is this cartoon saying. So you all know that 2022 Nobel Prize was given to Clauser. Clauser, Aspect and Zeilinger. These three got Nobel Prize for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. That is this foundational thing, and Einstein's Edenkan experiment, it brought out what is entanglement. And if entanglement is there and it gives me that universe is weirdest, it means it is different than what we thought. What can we do with it? That's we get into business now, and you start doing what is how different it is from our classical probabilities, what is the logic behind it, and how I can improve the algorithms that are allowed by classical computers, and how I can improve it using quantum theory. That's what is today's era. So for that, we started with foundations without asking for what is the application, but we got a technology, new technology, which is coming up. So these are some references here, which I have used for my talk. Okay, so I will leave it, you can note down. So the first one is Einstein's paper, and then I found this a good one, that is Chaturvedi, Mukunda and R Simon resonance article in 2006. It gives a nice, I have used it in many parts of my lecture, and David Bohm gave a new example than what Einstein used. Infinite dimensional example, we will be finding it difficult. That is, Einstein in his paper, he had given thought experiment involving measurement of a position and momentum. They are non-commuting. He chose a state which is infinite dimensional, that is like a wave function in x and t, write it in terms of momentum, which is going to be mathematically little messy. So I am taking that. David Bohm gave what I presented as a spin up, spin down or singlet state. That example is David Bohm. And then some historical things are given by Pius, Niels Bohr's times. So Copenhagen interpretation and such things in physics, philosophy and polity. And this is another paper by Arvind, who is in Sir Mohali, but he is a Vice Chancellor of Guru Nanak Dev University now. So he wrote a paper on EPR paradox. This is in 2000 in resonance again. And Mermin, as I told you, his Physics Today article is very, very nice and very witty. So I think you will read these things. And that's it. I think I closed early because I want to go early. So anyway, it ended. So thank you. The thing is, I have some more, but I was thinking I may not be able to finish it. That is to start with quantum computation, what are the bits and other things. But it's a good time to end now, I think. So this is just to give you how we came up to this, which is never taught in class textbooks so far. So then when you kind of know what all happened with quantum theory, it gives us more strength to teach quantum theory with more confidence. So I believe in that. So when you teach students quantum theory, you yourself need not, oh, this is weird. No, it is weird. So we'll accept it and then teach. Any questions? Very early. I finished very early. One gantanu madlilla. Shall I? I have some more. Yeah. So I can do. No, I prepared, but I was not sure how much I can do. So just a little more I will do. That is to say, today's world. Today we have quantum circuits. So like we have to write a Python code and kind of things. So we write, say, what is 0? Our cat is written something like a dot here, that is the representation. And then I will combine all of it and make a circuit. So if I write like this, what does that mean? It is called a gate. All our gates are unitary matrices. That I should take. So some unitary matrices are important. What is a quantum computer? It has all your qubits basically. I have qubits, and if I have how to create an entangled state or a superposition, that is one thing. If I have superposition, then I can do all the algorithms and play with it and show that, oh, quantum mechanics works this way. So, and then I can use some applications. What cannot be done in classical computer, can I do it using quantum computer? So, what I am showing here is 0 and 1, and this is a gate called Hadamard gate, and its matrix looks like that. And what does it do? It will create a superposition of 0 and 1. I have 0, fine. I have 1, fine. 0 and 1 can be combined together to create a superposition state. That can be checked. If I put a 0, if I put a 1. So that is the gate which is Hadamard here. And I have a rotation gate, anything unitary. I have to take unitary matrices, I told you. This is also a unitary matrix. This is also a unitary matrix. This is what cos theta by 2 minus I sin theta by 2. This is a unitary matrix. And this matrix is called a rotation gate. So I can have it and I write it like this in our whatever is the code. Whatever, when I write it, Rx pi by 2 means theta should be pi by 2. Rx with some value means it should be theta there. So now there is a theorem which says that, okay, this is another one. I have talked about single qubit unitary transformations here. Now I will tell you what is 2 qubit unitary transformations. One of the 2 qubit unitary transformations is called C0 gate. So C0 is, it looks like this matrix. I will tell you a little more just if I have time. It looks like this matrix. It's unitary again. So what it does is what I will tell you a little more. So now I have unitary operations to create anything and state evolution. Everything is done by unitary. So people have proved a universal theorem that with basic qubit gates like this, and if I have a C0, pile them up. So you can have different levels. You can create any unitary on universe. So that's the theorem. So you will get multi-qubit, n qubit unitaries using only a few single qubit and a two qubit gate. That's what is given. That means you can play with it and have a different unitary matrix which operates on a qubit. So I will learn only these gates is what you can declare, and then think about which is a good gate. Now in addition to creating a state and evaluating it, I have further things. The further things are measurements. I only have Z measurements allowed. Z measurements means it is this matrix. Z is this one, 1 and minus 1 is the value for this. Z has plus 1, minus 1. It is like our spin. But I don't talk quantum mechanics now. I use a quantum computing language. Z means Z gate in quantum computation. Z gate is nothing but a Pauli matrix 1 minus 1 which has eigenvalues 1 and minus 1. And when I do a measurement, I get either, this is symbol of measurement, and I get either plus 1 or minus 1. So I write 2 lines. 2 lines indicate that 2 values are possible for that. So now, okay, this is what is Hadamard is I have shown you that this Hadamard matrix can act on 0. It will create a plus state. Plus means 0 plus 1. So okay, this is, I will skip it. And then what is C0 gate? C0, what it will do? Just to explain, 2 qubit gate which is very important. This gate, I have to have 2 qubits. Single qubit, 1 qubit is called a control qubit, language computer science. Other qubit is called a target qubit. That is 2 bits are there, but now I have 2 qubits. So if I have a control qubit in 0, target qubit in 0, before I feed it to the gate, unitary operation is waiting. Before I have a 0, 0, then I have a control, that is doesn't change, but target will also be 0 here. But if I have a control in 1, the target will change to 1. It flips. So that is the way my gate is designed. I can create it, I can check it. So this is called a C0 gate. If I have 1 here, this 1 will become 0. That's the action of a CNAT gate. Now, with this is given in Wikipedia. So now CNAT gate, what does it do? Now I will take a general example. What is the general example? My 2-qubit state has this particular form. Why? 2-qubit state lives in a 4-dimensional Hilbert space. Basis is 0, 0, 0, 1, 1, 0, 1, 1. This is most general state. And I will take 0, 0 will not change, 0, 1 will not change, 1, 0 will become 1, 1, 1, 1 will become 1, 0 if I subject it to a CNAT. CNAT gate's action is defined like this. Now, the CNAT gate is represented by, I have shown it already, and circuit symbol also I showed it in one page. So now, I want to create Bell states. How do I create? Using my circuit language. That is, Bell states are created with photons and all that, but I want to learn the mathematical circuit language to create a Bell state, entangled state. So how do I do it? So I will start with, I want to create some Bell state. What do I do? In order to construct the 2-qubit Bell state given like this, there are 4 Bell states. I decide to create what is called as phi plus AB, this state. Both 0 or both 1, like how I showed you 2 horizontal and 2 vertical photon states. Now I will say, suppose I feed what is a 0A. I feed it as an input to the head-and-node gate. What will head-and-node gate do? 0 is fed, it creates an output state which is a superposition plus A. What did I do? This is a error here. It should be a 0A plus 1A. This is an error, so don't take it. So I get a 0A plus 1A. Now, when the states plus A and 0B, I have one lead, I have only 0A, and then I have a head-and-node, and other lead, I have 2 qubit leads, another lead I feed a 0A, let us say. Another state is 0A, 0B. A is this, B is this. Now, I subject it to CNAT gate with A being the control. If A is 0, B doesn't change. If A is 1, B will change, as I told you. So, resulting state is, if it is 0A, 0B will be there, 0A, 0B. Plus 1A, 0B is there, 1A, 1B. So, that is the state. So, I have to have a head-and-node gate, I have to have a CNAT gate to create what is 2-qubit entangled state, circuit language. Where is entanglement created? It needs a joint operation, never a single operation. So we should know that entanglement cannot be created if 2 parties are far away and nothing done. I have to create it here and then take them away spatially. Then I can see all miracles to happen. So now this is one example. Now I have X gate, Y gate, Z gate, which are also unitary. So I can use them to convert one Bell state to another Bell state. That is, if I take this same state, this state, I take this state and I will apply a sigma 1. Tensor identity means only on first qubit apply a sigma 1. How does sigma 1 work? I didn't write sigma 1 anywhere, but I will tell you. Sigma 1 means if I have a 0, it goes to 1. If I have a 1, it becomes a 0. That's all is the sigma 1 operation. So now if I apply sigma 1 on first qubit, that is A qubit, and B qubit, nothing is done, then you will see that it is 1 over root 2, 0A becomes 1A, 1A 0B, and here 1A becomes a 0A. This is what is called as a local operation. I didn't change anything, but the state became a different state, which is entangled still. A local operation cannot change entanglement value, but it can change the structure. States can be different. I can go from, oh, this state is not useful, another Bell state would have been useful. I can create it by local operations. So this is sigma 1 tensor product identity. If I take, what is this? I will take, this is phi plus or minus AB. What is phi plus or minus AB? I have written here 4 Bell states. Okay. Phi plus or minus is 0A, 1B, 1A, 0B. If I take this and again apply a Pauli operation. Pauli operation on A bit, A qubit. What will happen here? The 0, oh, what did I do? Wait a minute. Sigma 3 is what I apply, 5 plus. Sigma 1 will give me, okay. So, what I want to tell you is if you sit and work on it, you can create all 4 Bell states. How? What did you use? You used only a Hadamard, you only used a CNAT, and you used X gate, Y gate, Pauli gates, but written in the language of quantum mechanics, tensor products and all that. This is mathematics, that is circuit, but you get the output of all 4 Bell states can be created. So that is one thing, and these are the circuits. Like how I told you, one is I simply used 0, Hadamard and a CNAT control. So this is the picture and I get this state. And now I have 0, 0, X gate is used, Pauli gate, and then Hadamard and this one. Okay, this will give me psi minus, psi plus, psi minus. Okay, I am not sure. I should work it out. Maybe there is a error here because plus minus while writing I would have done something. So this is 0, 0, H here, X here. So I can create something else. X here means it is identity tensor sigma X. Identity, nothing on first qubit, A qubit, but second qubit should have a X. Then I get this, and phi minus will give me a minus sign when both X's are used. Sigma X tensor, sigma X, both are using it, kind of thing. So this will create a Bell state for us. So I can just mention to you one more how we went ahead and then stop. So what I will tell you is, suppose I am given one single copy of a qubit, single copy. So can I create multiple copies? Because it is useful for me. I can create entangled state. One state is there, I keep on multiplying them by using a cloning machine. It's like a Xerox photocopy machine. So I keep a sheet, white sheet, and I can create copies. How many you want? I can create. Can I do it in quantum mechanics? That is, to use, given a single copy of the state psi, question is, can we manufacture multiple copies of the same state? That is one question. So I will prove that it is not possible because our resource, I have a currency. I can use my currency. If it is lost, then I can't use it. So there is a natural way in which we can prevent it. That is, nature prevents it. No cloning. Cloning cannot be done. To prove it, what I say is, we consider a blank sheet and my state. I want to get psi finally. A blank sheet should copy psi and I should get 2 copies of psi. If I have an entangled state, I keep on doing it. I keep getting psi, so many. Entangled states are useful for my purpose. I will keep using them. Suppose I have this. We expect that with the help of a quantum copying machine, it exists, let us say. But the quantum copying machine should be unitary because states cannot go to it. Is linear transformation. All our operations should be restricted to unitary operations. Who says this? Quantum theory says it. So we have unitary operations taking one state to another faithfully. So it's a linear operation. So if I say that, I will take a unitary, that is a copying machine. It takes psi blank to psi. Assume that it takes psi blank to psi. Now a perfect copying machine, does it depend on the sheet I put? Another sheet if I bring, it should copy, no? So I will take a state phi. It should give me phi. Okay? So now for every other state also, if I take an inner product of the two, scalar product, I will get psi phi is psi phi mod squared, both sides, if I take it, which is wrong, which cannot happen. So if I have a cloning possible, these two are true. These two are true. And if I take left hand side, psi blank, phi blank, unitary acting on psi blank, phi blank, and then take a inner product. Blank will give me 1. Psi phi will give me psi phi. That is, I should know how to write a psi and take a inner product. That is, close it from left hand side. I didn't work it out explicitly, but left hand side gives me a psi phi. Right hand side has psi phi squared, mod squared. When is it true? It is true when psi-phi is 0. That means I can only clone orthogonal states, not all states. Orthogonal states can be cloned, but not anything else. So orthogonal states means my machine is not working. It only copies 2 sheets. Then it doesn't work. So we don't have a cloning possible. This is a no cloning principle in quantum computation. Having said that, people did not sit quietly. They used a way of, if I have a state here, I will send it to somewhere else. That is what is called as teleportation. I will not discuss it in detail. So in quantum teleportation, for me, now it is a circuit like this. That is to say, I should have something in one lab, I should teleport it to some other lab. It is possible. That is not cloning. What question arises is, if I can't copy a state, can I send a state from one place to another? It is possible. Quantum mechanics helps you. But that is with the help of an entangled state. Is what is the folklore now. That is called teleportation. And this is the circuit for it. And one has achieved it. But details I think I will skip for now. So we use this and make a measurement. And finally, I am going to get what is teleportation. So I will not talk about it. But it is a cartoons can be shown. So it is like saying, I have Alice has a yellow photon, Charlie has a pair of blue photons that are entangled. Charlie is a preparer of states. He prepares an entangled state, and what he does is one blue photon is given to Alice, one blue photon is given to Bob. And what does Alice have? She has a yellow photon already, and she has a blue photon given by Charlie. And Alice's blue photon has an entanglement with Bob's blue photon. So there are 2. So photon A is delivered to Alice, photon B is delivered to Bob, and Alice also has a photon which is yellow. So now Alice and Bob's relationship is cordial, but somewhat distant. They are far away. They can talk over a phone, no problem, but they cannot do anything. They are far away. So now what Alice does is, along with her blue photon, yellow photon and blue photon, she can do a measurement. In her lab, she can do a measurement. Measurement is well defined in quantum theory. She does a 2-qubit measurement, not a single qubit measurement, on her side. A, P together, she does a measurement. She has got a result and she informs Bob about her measurement. Just immediately, Bob before was a blue. After this measurement is conveyed, Bob's photon is different. What is that? So you will see that Bob gets a yellow photon without doing anything. Alice did some measurement and Alice's yellow photon has gone to Bob, which is possible by whatever calculations I showed, whatever circuit I showed. So today's situation is the idea of quantum teleportation was first presented in 1993, theoretical, and teleportation was first realized experimentally in 1997, and in this experiment Zeilinger, one of the Nobel laureate, is involved, and then later it was demonstrated in atoms, ions, electrons and superconducting circuits. So it is photon, one photon, yellow photon has gone to Bob's lab. That's what it is. Now can we do, electron is massive particle, it has a mass. Can I send a photon and put it in a electron? That is like photon, massless object to massive object. People have done that too. Massive to massive. So tomorrow I may get teleported to Bangalore without traveling. So that may become possible. Long way though. But that is what is kind of tried. So record distance for quantum teleportation is 1400 kilometer. And China has sent such teleportation from Earth to a satellite. They have created a satellite for this particular purpose, and this is Jian V. Pan, who was a student of Arthur Zeilinger. He has done such a thing, 2017. So these are some other things. They have created a optical fiber, and these are 2 entangled photons and 600 meters. Various teleportations have been reported. I don't know what is the situation in India. I think it is some 100 meters, one lab, PRL, Physical Research Laboratory, two different rooms which are opposite, they have tried to do that. That is what is reported by G.S. Agarwal's, one of his students. They have done that there. So, RPC. So, they have done something in PRL campus. So, these are, Zeilinger's group had done much more. They have kind of teleported 3-particle systems, 150 kilometers, lot of experiments. This is what gave a Nobel Prize for this. And today we are able to use single photons, single quantum systems in different platforms, nitrogen vacancy centers, diamond vacancies, and NMR and varieties of things. It's better we be aware and we try to learn some things little by little, step by step, and try to do these things is what I thought. So I don't want to talk about these things. I have this with me. That is, I don't know how much time I will take, so I have whatever I have to say. How quantum computation is different from classical. Only then I can make use of it. So we have to learn something more. So that is another story. So maybe some other time I get a chance to talk to you. So today it will be good to stop with this information, not that information.